Another way of doing it is to basically say, let's say that I have an arbitrary graph, right, with some many vertices in it, right, with correspondingly many edges. For each edge in the graph, write down the constraint x. Let's say the vertex goes from some node I to j, right. Xj must be greater than or equal to xi plus di minus nij times t, where nij is the number of token delays present on the edge between I to j. Okay. And in general, if I write down all of these things and then sum them up, right, what I will find is that I will ultimately end up with something which looks like this. I will end up with a set of many different constraints, right, and in each of those cases basically I will end up with t must be greater than or equal to summation of di divided by summation of nij, right, over where the summations are essentially over a closed cycle in the graph, right. The di is essentially the total execution delay through the graph, through the cycle, and the sigma nij is total number of token delays in the cycle, right. So in other words, it is possible to just write down this set of constraints and somehow maybe from that I can get a value for what this t is going to be. In practice, it turns out that an alternative way of looking at this is to say I am not going to actually go about computing this for all loops. In other words, identifying all the loops is basically the problem that I am having to deal with. So rather than trying to identify all the loops and then compute this t that way, another way of doing it is to say, assume a value for t, right. One possible value could be just summation of di over all nodes in the graph, right. This is obviously very pessimistic, but the point is choosing a large value of t is always safe, right. That is like saying that if I choose a large clock period for running a synchronous digital circuit, it is always guaranteed to never have a setup violation, right. As long as my clock period is large enough, in other words, as long as I operate my circuit slowly enough, I will never run into a problem in terms of timing. Okay. So choosing a large value of t to start with is always safe, and then I can go through check all the constraints of the form xj greater than or equal to xi plus di minus nij into t. What do I mean by check the constraints? The problem that I have over here is the xi values are unknown. Okay. So over here what I can do is start with all xi equal to 0. If there is a constraint violation, set xj equal to xi plus di minus nij into t for whatever t that I have chosen at the moment. Okay. This step has a specific term associated with it, not in the context of signal processing or in data flow graphs. It comes from the domain of normal shortest path algorithms in graphs, right? This is a step called the relaxation step, right, or a relaxation of a constraint, right? And in particular, this is used in something called the Bellman-Ford algorithm for finding shortest paths in a graph. Okay. Effectively, what it is saying is, this is one way by which I can try and arrive at a suitable value of xi's. Okay. Now, what will happen as a result of doing this? Initially, I might end up with choosing one value of, initially all my values of xi were 0. If some particular constraint, edge constraint was violated as a result of doing this, I will have to change that xj. I repeat this n number of times, where n is the total number of nodes in the graph. Okay. By that time, I should have got to the point where all my constraints are satisfied, and that is guaranteed because I have chosen my t large enough. Okay. I can't prove that within this class, but if you look up the way that shortest path algorithms work, you can sort of understand why this works, right? If I repeat this process of relaxation a maximum of n times, where n is the number of nodes that I have in the graph, it is guaranteed that I will be able to find a suitable set of values of xi, okay, provided my t is large enough. Okay. Now, if this works, I can try and reduce the value of t. And try again. That is to say, go back to checking the constraints and running this. Okay. So, by sort of iteratively going on reducing this value of t, I can eventually arrive at the smallest value of t for which it is possible to find suitable values of xi, right. I can go one step further. You can think of, you are probably already familiar with the idea of binary search, right. I can actually use binary search over here. So, basically if one particular value of t is satisfied, then I can straight away go to t by 2 and try again, right, then t by 4, let us say t by 4 fails, then search between t by 4 and t by 2, keep on bisecting until I can get t to whatever level of accuracy that I need. Okay. This is a practical algorithm, it can be used, it is not probably the best possible algorithm, but it is one of those things which is intuitively easy to understand why the thing works and how it is basically trying to find a solution to a set of constraints. Okay. So, to summarize, what we saw was, you can think of the iteration period as basically being the time between successive iterations of a data flow graph. Any given token delay on an edge can be considered to be saying that I need the data from one iteration earlier, and therefore the constraint that needs to be satisfied on that particular edge is that the execution time of the target must be greater than or equal to the finishing time of the source minus whatever number of iteration delays are present. And if I have a graph of that sort with iteration delays present on the edges and I have cycles in that graph, then there is actually a fundamental constraint on what is the minimum value of t that can be used for the graph. How can you find it? This algorithm is a general way of solving it, but a simpler approach, especially for signal processing systems, is probably going to be just identify the loops in the graph, compute the average sigma d by sigma n, find the maximum among all of them, and that is your iteration period bound. Okay. So, like I said, this is sort of the theoretical basis for what is the best possible performance that I can get out of a given data flow graph under a certain constraint of technology. Keep that in mind. My DA values are constrained by technology. So, in other words, if I move to a better technology, right, 28 nanometers, 20 nanometers and so on, I will probably end up with faster execution units. That itself is sufficient to reduce my value of t, but that is not what we are interested in. Okay. Subject to this constraint of technology, this t is a property of the data flow graph. It is a theoretical minimum bound. How do I actually achieve it in practice? That is a problem, because you might find that in reality, in order to actually get close to that bound, I need infinite amounts of hardware. Okay. So, what we are going to do next is to look at more practical situations. If I have a limitation on the amount of hardware available to me, what is the best throughput that I can get, and what are the ways by which I can go about improving that throughput systematically. Okay. We will stop here for now and continue with those topics tomorrow.